The oxidation of aldehydes to carboxylic acids can be achieved by an enzymes or a class of enzymes known as aldehyde dehydrogenases. Now, aldehyde dehydrogenases usually have an active site cysteine residue. It's believed that this active site cysteine residue serves two functions. One is to form a thiohemiacetal, which basically anchors the substrate, the aldehyde, to the enzyme. It's essentially covalent catalysis. And it also activates carbon 1 of the aldehyde for hydride transfer. At least in one of two possible mechanisms that have been proposed for this. Let's look at these two mechanisms. The first mechanism is a covalent catalysis mechanism. That has been proposed. Now, in the covalent catalysis mechanism, there's an active site cysteine. I'll represent it as follows. And there's an active site lysine or some other group that behaves like an acid, and there's an active site cysteine group. I'll show it deprotonated, and we have our reacting aldehyde. Now, the cysteine sulfur attacks, does an acyl substitution reaction, or starts an acyl substitution reaction, does an addition, the addition part of acyl substitution, generating our base from the conjugate acid, and this is now we're attached to the enzyme. Remember, this is enzyme. So this is our thiohemiacetal. Now this thiohemiacetal, this hydride has been activated so it can leave. So there's an NAD plus that accepts it, and that generates the thioester. Put an R group here, sorry. And we still have our active site base here. That sees a water molecule and hydrolyzes. Again, acyl substitution. I'm going to show the cheater mechanism. Remember, this expands to a tetrahedral intermediate and then collapses back, kicking out the sulfur group. That generates our carboxylic acid and regenerates the catalyst, the enzyme. So we converted an aldehyde to a carboxylic acid.